Good day, everybody, and welcome once again to my channel. By the way, it's been such a good time of learning. I hope that you've been enjoying the other lessons. For those of you who haven't subscribed, where have you been? Okay, we've been learning quite a lot, and there are many other videos that I've produced on many topics in physical science, and I hope that you are benefiting from them. All right, so today what we want to do is to cover the photoelectric effect. And what I want to do is I just want to make it as simplified as possible, okay? So that you can be able to understand it and be able to apply it, particularly in an exam situation. Okay, so let's dive right into it. Okay, right, so we want to start basically on what do we mean when we talk about the photoelectric effect? Okay, so when we use the word photo, normally we're referring to taking photos and pictures, but this time remember that photo has to do with light. Okay, so this is basically a compound word that has to do with light as well as electricity. So the relationship between light and electricity. Okay, so essentially, what happens in the photoelectric effect is that we are using light energy, okay, in order to produce electrical energy. So let's talk about how exactly that happens. Let's talk about light first of all. So we know that light has got a dual nature. So when we talk about photo, remember, we are simply referring to light. Okay? Right. So light has got a dual nature. And the two natures of light, in fact, if you don't mind, let me just change the color of the pen that I'm using. Right. So the two natures of light is that first of all, light can behave as a wave. So the wave nature of light is what gives us things like reflection. It's what gives us things like refraction. Okay, and probably you've learned all about that in the previous grades, right? So this is where we know that light can or does have a wavelength, and it also has frequency. Okay, so now what we now notice, okay, or what we can learn from this is that now remember that we know that frequency and wavelength are simply going to be related. They're inversely proportional to each other, right? And this time around, it means that frequency multiplied by wavelength gives me the speed. Now, if you remember in the the Doppler effect, right? In the Doppler effect, what we had was that when we use the speed here, this had to do with the speed of sound in a medium, right? But this time, remember, we are not talking about sound, we are talking about light. So as a result, the speed here is now the speed of light in a vacuum. And that speed is actually 3 times 10 to the power 8 meters per second. Okay? Right, so now we know that light can behave as a wave. So that's the wave nature of light. When we can actually relate the properties of light, okay, in terms of a wave, we know that we can talk about frequency, we can talk about wavelength. Now, what does this actually have to do with anything? So remember that when we're looking at the spectrum, right? So if we have to look at, say, for instance, the visible spectrum, all right, where we've got red, orange, yellow, green, blue, indigo, if you think about it from a perspective of a rainbow. So what we do know is that red has got the lowest frequency, meaning that in the visible spectrum, red has got the longest wavelength. Okay, so red has got the longest wavelength, and as a result it has the smallest frequency, right? But when you look at violet, for instance, it's got the highest wavelength in the visible spectrum. All right, so it means that the frequency of light increases as you move towards violet. Okay, but please also remember, bear in mind that you also have the not the invisible spectrum. So after violet comes ultraviolet, which is UV light. You get that particularly from the sun or fluorescent light bulbs. Okay, so that's UV light. And you've got X-rays. Okay, so those are other right. And remember, the more we go into that side, and obviously with the penultimate being the gamma rays, right, which are the most dangerous forms, or which is the most dangerous form of radiation. Okay, so this obviously would have the highest form of frequency. Sorry to draw it so small. Right, so in this case we are referring to light in this case as a wave. So we can talk about its frequency, we can talk about its wavelength. Okay, all right. And obviously before red here you've got infrared. Okay, you get that from cell phones, or maybe quite relevant lately. We've been using those temperature sensors, right? Whenever we go to malls, or whether we go to school, or whatever the case may be, we use those infrared temperature sensors, and that has obviously higher, even longer frequencies, longer wavelength rather, than red. Okay, and obviously a shorter frequency. However, when it comes to the photoelectric effect, okay, we no longer now are looking at the wave nature of light, even though we're going to intertwine the two to some extent. But what the photoelectric effect has to do with, it's the particle nature of light. So the behavior of light as a particle. Now, normally we say that because light has these two natures, it can behave as a wave and it can behave as a particle. We talk about the duality of light. Duality, so meaning dual just means two. So those are the two natures of light. And under this is where now we are looking at light as a photon. Now, I'm going to try and break this down and make this as simple as possible. Okay, so now what's a photon? Essentially, when we talk about a photon, it's a packet of energy. All right, I want you to imagine, so anytime that we've got light that is emitted, you can think about, let's say we are irradiating light onto a substance here. You can think of little packets of energy being emitted. Okay, those little packets of energy being emitted there, and these little packets of energy are referred to as photons. Okay, right. Now, ladies and gents, I want you to please just stay with me as I go through this. Okay, right. So now, under the photoelectric effect, we know that we now have light as a packet. However, as particles rather, and those particles are photons, which in this case are little packets of energy. Now, how do we determine that energy? Well, that energy is related to the frequency of light, and you'll see why I said we can actually intertwine the two. So Einstein simply said, well, we can determine the energy of a photon of any light. Well, it's directly proportional to the frequency. Okay, so if it's directly proportional to the frequency, it means the higher the frequency, the higher the energy of that particular photon. Well, that's why we had to go through this, right? Because it means if we are looking at, for argument's sake, blue light in comparison to red, it would mean that blue light has got a higher frequency than red light. And because it has a higher frequency than red light, it means that the energy of the photons that are emitted by blue light would have a higher energy than the photons that are emitted by red light. I hope that makes sense to some extent. Okay, right. Now let's go and look at how then do we apply this under the photoelectric effect. As I said, ladies and gents, the thing about the videos that we always produce is that what I try to do is to make the information as accessible as possible. So I want to try and make it as simple as possible such that you understand it and keep it to only what's relevant to your curriculum. Okay, so suppose we had a metal, all right, on which we are irradiating light on. So it means light is shining onto this metal. Now, any metal has got electrons that are obviously trapped within it, or if you want to look at it, those electrons belong to atoms. Okay, so they are attracted by the nucleus of that particular atom. However, in a metal, because they are so close together, it almost seems like a sea of electrons, okay, that are almost moving about freely. That's why it can conduct electricity quite easily. Okay, so what simply happens when we shine a light, okay, or when we say that light is incident, to use the term that they normally use, right? So it means this is light that is entering any surface. Now, I want you to think of 3 conditions that are going to take place, and I'm going to talk about those conditions. Okay, right, and you'll see why I'm referring to those conditions in just a few. So suppose we were using light, red light. I'm just making an example with this. Suppose I'm using a red light. Now I want you to imagine, in this case, these electrons would require a certain amount of energy for them to be released from the metal surface. Okay, so in this case, if I use a light, okay, that has lesser energy than what is required to emit these electrons, those electrons will not move. I want you to think of yourself, if you were taking out a stump of weed, okay, not that kind of weed, right? Right. If you are taking out a stump of weed from the ground, if you were trying to pull it out, obviously there's a certain amount of energy that you must actually put in to be able to take that weed out, isn't it? Okay, so think about it. These electrons are holding on to the metal. They are inside the metal, okay? And in this case, they are attracted by the atoms, all right? And nucleus of the atoms. And as a result, what will happen? They will remain there. But then the photon comes in and gives these guys energy. But if that energy is not sufficient, okay, right? So those electrons will not be able to move. Now, ladies and gents, I want you to please stay with me and see. I want us to talk about this energy. Now, the energy that is emitted by the photon is calculated based on Einstein's equation, right? E is equals to hf. Now, look at this. This is the energy of the photon. This is what we call Planck's constant. It's just a constant. By the way, ladies and gents, I want you to note you are always given Planck's constant in your data sheet, right? So in this case, you've got h, which is Planck's constant, and you've got frequency in this case, which is obviously related to what we were talking about there. Okay, But because we also know that frequency is related to wavelength, we can also say, well, we know that to calculate the energy of a photon, we can simply say H multiplied by, remember, F is c over lambda. So in this case, that is going to be c, which is the speed of light. Remember, we referred to that earlier on, and divided by the wavelength of that particular light. Okay? Right, so this is how we calculate the energy of a photon. Now, ladies and gents, then we've got what we call the work function of the metal. Now, what is work function? We normally use the symbol omega 0 for the work function. Well, we say the work function is the minimum energy that you would require in order to emit electrons from the metal surface. Now remember, I said if the energy of the photon is not sufficient, right, then we will not be able to emit electrons. Now think about this now. Let me put it in a way that is going to be simple. So if the energy of the photon is less than the work function of the metal, so we call this the work function, okay? So is less than the work function of the metal. What happens? It means no emission of electrons takes place. Okay? Right. Now note, so that's going to be our first condition. So condition number 1, if the energy of the photon is less than the work function of the metal, okay, we say, well, in this particular case, there'll be no emission of electrons. Electrons will not move in any way, okay? So there's no emission that takes place. Number 2, if the energy of the photon is equal to the work function, I want you to think about Newton's laws in a sense, okay? If I ever wanted to lift something, right, how much force must I use to actually lift something? The amount of force that I must use must at least be equal to the weight of that particular object, okay? So suppose I wanted to lift a stone or a rock, okay? The amount of force that I must use must be at least equal to that force. Now, when that amount of force that I use is equal, I will be able to lift, okay? So in this case, we say in this, if the energy is equal to the work function, it means that if the energy of the photon is equal to the minimum energy that is required, what will happen? It means that the electrons will simply lift, but they will not go any further than that. So in this case, we say that the electrons will be able to lift, but still there'll be no movement, okay? So in this case, there's no movement, right? So they'll be able to lift. Look at my spelling for movement, sorry. So there'll be no movement. Okay, sorry about that. Okay, so let's talk about the third condition now. I'm just going to move the page that I'm using. Okay, so the third condition, and this is probably where we are going to spend most of our energy on. This is where we are probably going to spend most of our time. And you'll see when we do calculations, you'll see that most of them are based on this. Now, when we find the energy of the photon when it's greater than the work function of the metal, okay, then what happens? So the photon is incident, it comes into the electron, it gives it so much energy that the electron gets excited, and what happens? Bing, out goes the electron, it starts moving. Okay, so obviously the greater the amount of energy, the more the electron will be actually able to move. So in this case, not only are we going to lift the electrons, okay, right? Not only are electrons going to be emitted when we're talking about lifting, but in this case, electrons will be able to move, okay? So we not only have now just the lifting of electrons, but now we also have movement of electrons. Okay, so when the electrons are able to move, what do we associate energy that's associated with movement? Of course, we call that kinetic energy, EK, right? For some of you, maybe may prefer to use K. It doesn't really matter. Now, I'm just going to move this a little bit. So it means that when I look at the energy of a photon being greater than the work function of the metal, so I know now that the energy of the photon will not only cause a lift, which is the work function, okay, right, but it will also cause kinetic energy. So it means because that energy is in excess, it will overcome the work function, and in this case it will also cause movement. Okay, right, now ladies and gents, I want you to notice what I want you to see there, right? In this equation, all that we need to be mindful of is what represents what there. Okay, right, I'm just going to utilize the space on my left hand side, okay, and I'm going to just write over there. I want you to actually notice that whenever we talk about the energy of a photon, right, so we talk about that equation. We said E is equals to omega 0, which is the work function, okay, so that's omega 0, which is the work function, plus the kinetic energy. Now, in this case, just to unpack the equation, I want you to note this E, this energy here, has to do, we said it has to do with the energy of the photons. And remember, how do we calculate the energy of the photons? All right, we said E is equals to HF, or you can say HC over lambda. All right, and then this here we said has to do with the work function. Now, okay, let me, right, so this has to do with the work function, okay, function, all right, okay, right, so this has to do with the work function, all right, and here, by the way, remember, how do we calculate the work function? Okay, I'll come to that in just a few. Right, so, and here we are dealing with the kinetic energy. And remember, what is kinetic energy? By the way, what is moving? First of all, let's talk about that. What is moving are the electrons. And by the way, don't be alarmed. We say EK max. This is the maximum kinetic energy. Of course, it will depend on several factors. So that would be the maximum kinetic energy of that particular electron. Okay, right, and please remember that kinetic energy, how do we calculate it? How do we calculate kinetic energy? This is half mv squared. Now, if you think about that, remember, what is moving? It's the electron. Okay, so this m here has to be the mass of the electron. And by the way, just to show you, ladies and gents, you are given the mass of the electron. Usually when they give you your data sheet, right, you've got the mass of an electron there. Let's see, so you are given ME, that at the bottom there, that's the mass of the electron. That's 9.11 times 10 minus 31. Also, just what I wanted to show you, you've got Planck's constant there, the H value, okay, and that H value is 6.63 times 10 minus 34. Okay, right. So just remember you are given all of these values. And by the way, just so that you also see it, you're also given the speed of light in a vacuum. Okay, sorry about that focus there. Okay, so the speed of light in a vacuum, you're given that as 3 times 10 to the power 8. So all I'm trying to show you, ladies and gents, is that everything that you need in order to calculate, to work out rather, past exam questions in this particular section, you are always going to be given. Okay, right. Now, quickly, I spoke about the work function here, but exactly how do we calculate the work function? Well, we say the work function will be h multiplied by f0. Now, if you remember, I'm just going to bring you back here. Where do we get this work function? We said, well, remember, when the energy of the photon is exactly equal to the work function, there'll be a lifting of electrons. So they won't necessarily move, but they will simply lift off the metal surface, right? So now we say, well, the frequency that caused, or the frequency of the photon that caused the electron to lift, we simply call that the threshold frequency. I want to make an example for you quickly. Suppose we say, okay, let's take red light and we shine it onto this metal surface. And we realize, okay, nothing happens with red light. What does that mean? It means that the energy of red light would be less than the work function of the metal. And then we use orange light. Say the same thing happens, okay? And then we realize, no emission takes place. And then all of a sudden, when we take yellow light, okay, all of a sudden the electrons lift. Then we can say, oh, so it means yellow light, the energy of the photons of yellow light are equal to the work function. Now, please, I want you to note, but remember that yellow light has got a frequency, right? So then we call the frequency of yellow light for that particular metal, we call it we call it the threshold frequency. I want you to note. So the work function will be h multiplied by the frequency of the photon that causes it to lift. So as a result, the work function is h multiplied by f0. So we call this the threshold frequency. Now, what is the threshold frequency? We say it is the minimum frequency required in order to emit electrons from a metal surface. Okay? So I hope that you can actually you get the gist of what I'm trying to show here in this lesson. Okay? What I want to do to seal this lesson, let me just take 1 or 2 questions from past exam, and then what we'll do is let's try and answer these questions in relation to what we've done. Okay. All right. So let's take the DBE 2019 paper. Okay. So we're given there. By the way, this was DBE 2019. So that's the senior certificate or national senior certificate. So for those in South Africa, usually this is written in May, June, right? So they say a potassium metal plate is irradiated with light of wavelength 5 times 10 minus 7 in an arrangement as shown. So there we have it. We've got incident light. So this is light that is entering, okay, that metal plate. And what it's going to do is it's going to cause electrons now to start flowing, right? Now, notice the language. They say the threshold frequency. Now, remember, we said the threshold frequency, that's the minimum frequency required in order to emit electrons from a metal surface. So if you think about it, so this threshold frequency here will actually help us to determine the work function, isn't it? Okay, So because remember, we said that the work function will be Planck's constant multiplied by the threshold frequency. Now let's try to answer the questions together. Now, just as a side note, ladies and gents, I want you to please remember that every metal surface, or every metal for that matter, has got a different work function. What am I trying to say to you? I'm trying to say whatever metal that you use has got a different work function, and so they will specifically tell us the metal in question, like they did here. They told us that it's potassium metal, okay, and meaning that we will either be given the threshold frequency, or we will be given the work function, or we'll have to calculate it for ourselves depending on whatever question it is. Okay, right. So now, all right, so the first question, they say define the term threshold frequency. We know that's the minimum frequency required, isn't it, to emit electrons from a metal surface. So I'm going to start from question 10.2, and let's try to answer that together. Right, they say to calculate the energy of a photon incident on the metal plate. Now, we want the energy of the photon, ladies and gents. So we know that the energy of the photon, remember, we said that's E is equals to HF. So let's see what we are given. We are not given the frequency of the light that's irradiated, but they gave us the wavelength, okay? But please don't you worry, because we know that frequency is C divided by wavelength. And you remember this, F is equals to C over lambda, right? So that's going to be C divided by lambda, and let's calculate. So that's 6.63, okay, times 10 minus 34 multiplied by our C value. That's 3 times 10 to the power 8, okay, divided by our wavelength is what was given in the question. That's 5 times 10 to the minus 7, okay? And all that we need to do is just calculate. Okay, I'm just going to pull out my calculator over there, okay, and say, all right, so that's 6.63, okay? Just use this exponent button here because it saves you from a lot of work. So I'm going to say times 10, and then I'll say minus 34 multiplied by 3 exponent 8. Can you see how easy it is to use that button, right? Divide by, that's 5 exponent minus 7, okay? And I get a value there of 3.98, okay? So that's 3.98 times 10 minus 19 joules of energy. So what is this? This is the energy of a photon. Nothing difficult about that, ladies and gents, right? Okay. And then secondly, now they say, using a suitable calculation, prove that the emitter will show a reading. Okay. Right. What will cause an emitter to show a reading? Remember, what does an emitter reading? What does an emitter actually read? It reads current that is flowing. What will cause current to flow? What will cause current to flow? Obviously, it's the electrons that are moving, isn't it? Okay. So they are taking us to condition 3 in terms of the things that we discussed previously, right? So they are taking us to condition 3, where we found that in condition 3, remember that? So in condition 3, we remember that the energy of the photon was equal to the work function plus the kinetic energy. So it is where the energy of the photon is greater than the work function. Okay, right. So in this case, what we simply need to prove is that whether the emitter will show a reading. Now, there are several ways in which I can do this. I can prove that there will be kinetic energy, or rather that kinetic energy will be greater than 0. It will be a finite value, right? So in this case, let me do this. Would it be okay if I just calculated the work function of the metal. And if I find that the energy of the photon is greater than the work function, then I can conclude that there will be kinetic energy, right? So I'll start by saying let's calculate 10.3. Let's calculate the work function. But remember, ladies and gents, how do I calculate work function? Said work function. In this case, I'm given the threshold frequency. So I'm just simply going to say H multiplied by F0. Okay, so this is going to be 6.63 times 10 minus 34 multiplied by, okay, so they gave me the threshold frequency there as 5.55 times 10 to the power 14, that's hertz, right? And please remember, work function is energy, right? So let's pull out our calculator again, right? So we're saying that's Planck's constant, 6.63 exponent. Okay, please remember, when you press this button, you don't have to press that YX button, right? That's minus 34, okay, multiplied by, that's 5.55 exponent 14, okay, right, and I get a value of 3.68 times 10 minus 19 joules. Okay, right. Now, I can just simply say, well, to answer this question, because they didn't necessarily ask me to calculate the kinetic energy, but you can if you want to, and prove that it's a positive value. Okay, in fact, let me do that. So E would be equals to omega 0 plus Ek, right? Ek max. Now, please remember, the electrons that are irradiated are simply called photoelectrons. So please don't be alarmed when you see that word photoelectrons. Okay, all that it simply means, it's electrons that are irradiated, or it's the current that is caused by the light energy that is entering there. All right, so now this value E, we found that value 3.98 times 10 minus 19, and work function, that's 3.68 times 10 minus 19, okay, plus Ek. So Ek will definitely give us a positive value. Can you see that? So we will get a positive Ek value, or kinetic energy value. So that's 3.98. Okay, so that's 3.98. Okay, and when we take that to the other side, we'll subtract that. So that's 3.68 minus 19. Okay, and I get a value which is 3 times 10 minus 20 joules. Okay, right. So I get a positive value for kinetic energy, which simply means to me that there will definitely be a movement of electrons. What you also could have done is you could have just concluded, right? I'm just going to write it on this side. You could have just concluded, but I know that my E value, the energy of the photon, is greater than the work function. So therefore, it means that electrons will be able to move. Okay, so in that case, there will be movement of electrons. Okay, right, or therefore it means that kinetic energy will be greater than 0. Okay, right, so I hope that you get that, ladies and gents. Now, I just want to move quickly to a point that I very often get questions on, about intensity. If you don't mind, I'm just going to do this question, and I'll do a follow-up video on photoelectric effect and do some more questions on it. But I want to just conclude by just explaining about electrical intensity. Okay, so when we talk about intensity, right, now, ladies and gents, please, I want you to note, when we're talking about intensity, we are simply talking about the brightness of light. Okay, so we're talking about the brightness of light. Okay, so when we're talking about brightness of light, what it simply is related to is the amount of power that a light has. Are you with me? Right? So in this case, it means that we've got a light which has a specific or a certain amount of brightness. So when you increase intensity, I want you to please listen carefully. When I increase intensity, what happens is that, suppose, let's say we had electrons that were in a metal, and we shine a light onto it. Okay, what happens is that there will be a specific amount of electrons that are emitted depending on the power of that light, the brightness of that light. So suppose I was using a 60-watt bulb, okay, just for argument's sake. So when I use a 60-watt bulb, I find that for argument's sake, I'm able to emit 5 electrons every second. I'm just making an example with this so that you understand it. Okay? And we're using, let's say, blue light. Okay, so this is blue light, but the power is 60 watts. But now, let's say I still use blue light, but in this case, I use a brighter form of blue light. Now, ladies and gents, please note, if it is still blue light that I am using, remember that frequency has not changed. So the frequency of this light here and the frequency of that light have not changed. But let's say I use a 100-watt bulb. Okay, right? So here it is, I'm using a 100-watt bulb, but it's still blue light. How will it affect the irradiated or rather the emitted electrons? Now note, because frequency has not changed, it means that energy of the photon will also not change. So the photon of blue light at 60 watts is equal to the photon of blue light at 100 watts. Okay? Right? So please remember, it means that the emitted electrons will move more or less with the same kinetic energy. So nothing changes about the kinetic energy. So now we said, suppose that I was emitting 5 electrons per second. What will happen when I increase the intensity, when I increase the power, right? I will be able to emit more electrons per second. So if I was emitting, say, 5 electrons per second there, now when I use a high power bulb, I now will be able to emit more electrons per second. But please note, they are still moving with the same kinetic energy. I hope you can understand that, ladies and gents. So if I was emitting 5 electrons per second, you'll find that, just say for argument's sake, here now I'm able to emit 10 electrons per second, just for argument's sake. All right? So electrons are still moving with the same kinetic energy, but instead of emitting 5 at a time, now because I've got greater power, I'm emitting 10 at a time. Okay? So as a result, it means here I will have a greater photocurrent. Remember, what is current? Current is simply the rate of flow of charge. Okay? So it's the charge, so the amount of electrons that I have divided by time. So what have I done here? I have increased the amount of electrons that I emit in a given amount of time. So if I increase that amount of electrons, therefore it will increase the amount of electrons, the amount of current that is emitted. Okay, right. Now, just to help with that, so I'm just going to put it in a simplified way. If I increase intensity, all right, so obviously you can apply this for decrease as well, right? Just it will be the opposite of what I'm about to say. When I increase intensity, right, remember that kinetic energy stays the same because it's the same type of light. So when I increase intensity, I increase the number of emitted electrons per second. So the number of emitted electrons per second. All right, per second. Okay, let me write it over there. Right, so I increase the number of electrons emitted per second. All right, and what does it do? In this case, it will increase the photocurrent. Okay, so it means that my photocurrent should be able to increase. I hope you get that, ladies and gents. Okay, so it will increase my photocurrent. So in this case, please, I want you to always remember that. Okay, when they start talking about intensity, they are simply talking about the brightness. And when I increase the brightness, it does not affect the kinetic energy of the electrons, but what it affects is the number of electrons that are emitted per second. And that's exactly what this question was asking. They say the intensity of the light is now increased. Explain why this change causes an increase in the emitter reading. Okay, so exactly what we said. An increase in intensity will increase the number of electrons that are emitted per second. Okay, thus it will increase the photocurrent, and that is why we'll have an increased emitter reading. I hope that makes sense, ladies and gents, right? Now, just as a conclusion, remember, if I were to use, let's say, violet light instead of blue light, how would that change anything? Okay, if I were to use violet light instead of blue light in this case, what it would do is that it would, remember, violet light now has got a greater frequency than blue light. So as a result, when I use violet light, it will increase now not the not the amount of electrons per second, right? What it will do is that it will cause the electrons to now move with a faster or a higher kinetic energy. Okay, why? Because in this case, you've now increased the energy of the photon. Remember, the work function would remain the same, if we're using the same metal. So what will definitely happen here, that because you've increased the energy of the photon, then in this case, it will increase the kinetic energy of that particular electron, of those particular electrons. Okay, right. So I hope, ladies and gents, in our next session, when I do more past exam questions, you'll be able to grasp this, you'll be able to understand it, okay? And I'll do more graph questions that have to do with the photoelectric effect. Otherwise, I'm gonna keep it here for now, and thank you so much for watching. Please don't forget to subscribe for those who haven't, okay? And I'll see you guys next time on the next lesson. Sharp, sharp.